Hey everybody, we are here on Taylor polynomials. What I want to point out real quick is that we're not doing 9.2 in the book. It's 9.7. I'm just going to use somebody else's notes that have some good examples and things like that. A Taylor polynomial is an example of a power series, which we're going to learn more about power series in the next lesson. Basically, it's the same thing we've been talking about, right? Where maybe we used to have like 1 over n, and that's just like a series. A power series would be like there's a variable in there, right? Maybe like there's an x somewhere in there, and so that's a power series. Is you're adding a variable. What Taylor polynomials are good for, which is what we're talking about today, is approximating. This method is how is one way that your calculators calculate sine of different values, or cosine, or even tangent, like, or e and ln, all those complicated functions. That this is how the calculator is programmed to calculate it. It's pretty long to do it by hand, but it is something we're expected to know how to do. The cool thing is you've already actually done this in a small degree. So let's look at that with example 1. It says find the equation of the tangent line for f of x equals sine x at x equals 0, then use it to approximate sine of 0.2, and then we want to know if it's underestimate or overestimate, right? So if you remember, tangent line was y minus y1 equals m x minus x1, right? In this case, our x is 0, right? Our x1 is 0. Later in this chapter, I'm sorry to get sidetracked here, but later in this chapter, we're going to call this value c, right? We're going to say c is 0 because it's the center, right? It's the center, or the point of tangency, right? So what we could do is the same thing we always did, is first we need y1, which is we have to plug in the x, so sine of 0 is going to be in this case 0, equals m, which is the derivative, right? So in that case we'd have to find f prime of 0, which f prime is cosine, right? So it's going to be cosine of 0, which is 1. So this will be 1 times x minus 0, right? And you'd simplify it all and you get y equals x, basically, right? This is our approximation. And then if we wanted to approximate sine of 0.2, well, we would plug in, we would evaluate this at 0.2, right? We do y of 0.2, and we would get 0.2. And what we're saying is that this is pretty close to sine of 0.2, right? Like it's an approximation for sine of 0.2. And it's asking if it's an overestimate or underestimate. So I just want to show you, if you graph sine, it looks like that, right? And we are finding a tangent line through 0, which is here. And you can see, because we did sine of 0.2, which is on the right hand side, right? Sine of 0.2 is on the right hand side of this thing. Our sine is concave down, right? And so our tangent line is going to be on top, and so this is going to be an over approximation, right? It's going to be an overestimate. All right, and the last thing I want to show you on this is a different notation for this, right? So let's look at a different notation, right? So one thing we could do with this is we could go ahead and add that y1 to both sides, right? Which it's actually probably a better way to teach it in general. If you're going to teach an Algebra 1 student how to do this, it seems easier to write it this way, because then there's no solving required when you are done, right? It's just the y ones over there. And then we're going to try to write function notation, right? So we're going to write, we'll keep this as y for now. We'll talk about different notation for that. But remember, we were going to use c instead of x0 or x1, right? We're going to use the c for this. Like, we're going to call this c. And so to get this y value, you are basically just plugging in the c value, right? So this is the same as f of c. To get this m value, we were simply taking the derivative and then plugging in the c, or the x1, right? And then over here we just have x minus that c, which is, again, it's just the same as x1, right? And so here's like a different notation that you could do, right? So it's the original function evaluated at c, plus the derivative of the function times x minus c, and this will lead us into something in just a second. Okay, so let's just real quick graph so you can see what this looks like. Come on, calculator, there we go. So we're going to graph sine x, and we're going to graph our tangent line x, and you can see there's sine x, and our tangent line goes up like that, and you can see it looks like it follows the sine curve pretty well right there in the middle, right? If you look at like near 0, that tangent line is a pretty good approximation. We can also go ahead and just look at what sine of 0.2 is and see if our approximation was pretty good. Sine of 0.2 is 0.1986. We said it was 0.2, right? We're a little bit higher than 0.1986, so it was a decent estimate depending on how accurate you want it to be. That might suffice, right? And it's a lot easier to plug things into y equals x than it is to plug things into sine. Okay, so let's keep going. That tangent line that we came up with is actually called the first degree Taylor polynomial, right? It's a line which means it has degree 1. And we can even use higher degrees to get better approximation of non-polynomial functions near x equals c, which again is called the center or the point of tangency. So we can write not just a tangent line, but we could write a tangent parabola, or we could write a tangent cubic function, or we could write a tangent fifth degree function, right? And that's what we're going to do here right now, just an example. Let me delete those. I had to redo this. Oh, excuse me. Okay, so on our calculator, which we already did, we're going to graph sine of x. Use this window, right? So do this also, and then under y2, we're going to graph this function here by just successfully adding terms, right? So we're not going to do them all at once. We're going to keep doing each piece, right? So we already did the first term, the x. So now we're going to do the next term, which is x minus x to the third divided by 3 factorial. All right, we're going to graph that and see what that looks like. So there's sine, and then here's that thing that we created, right? And you can see that this, if you look in your graph, like this is a better approximation than the line was, right? Like it's following the curve even closer, and it goes out a little wider than the other one did. It's accurate farther away from 0 than the other one was. Okay, so it's going to add another one. Plus x to the fifth divided by 5 factorial. And then we can see how accurate this one is. There's our sine curve again, and even better, right? So it's getting closer to the sine curve as we go, and so we could do yet another one. Minus x to the 7th divided by 7 factorial, and we're going to get even better, right? Look how far, like in that middle piece, it looks identical to sine, right? And then, so you get the idea, like we could just keep adding and subtracting those terms. You see the pattern, right? And you could keep doing that and to get a better approximation. So let's answer the question. So what do you notice? We notice that like the more terms we add, the more accurate it becomes. Let's answer these. What's y1 of 0? Right, this is basically sine of 0, which is 0. Then it asks what is y2 of 0, which is basically plugging in 0 to this polynomial, which notice each term has an x, so you're also going to get a 0 there. It asks what's y1 of 0.2. That was our sine value. Let's go down here and just do that. It's 0. We're going to do a lot of decimals on this one today, so don't just round to 3 decimals for today, because we're going to try to compare exactly how it is. And then y2 of 0.2 is, let's go alpha trace y2 of 0.2 is going to give us 0.198669338. And so you can see, for as far as the accuracy of the calculator goes, they're identical, right? That doesn't mean it's perfect, right? Because if the calculator could show more decimals, then eventually our little thing would be off because it's not perfect. So you can see how it can give you a really good estimate of what the function is. I do want to show you one other thing. Let's look at a table. The first thing we need to do is change our table. Okay, we're going to start at 0, and our change in the table is going to be 0.1. So make sure you change your, if you're going to do this with me, change your this to 0.1, and then we're going to go to our table and look at some values, right? And so remember, y1 was our sine, and y2 is our polynomial approximation. And you look at those values and see that even up to 0.6, as far as accuracy of the calculator goes, like both y values are identical. Even up to 0.8, 0.9, 1. Here's where they start getting a little bit different. At 1.1, you can see that the numbers are slightly different, but even up to the accuracy of what you'd expect on the AP exam, it's accurate enough, right? And so the point I'm trying to show you here is the farther you get away from the center, the less accurate the approximation becomes, right? So it's only very accurate close to the center, and the farther away you get from the center, the less accurate it is. Let's just show you like an extreme example, right? Like at some point at 6.8, our approximation is giving us -57, and sine can obviously not be ever -57. So like the point is it's only accurate close to your center, right? So within a certain radius, which we'll talk about later, right? So the polynomial approximation is more accurate close to the center. And the farther away you get from the center, the less accurate it becomes. Okay, so here's the definition of where that polynomial we typed in here, where this x minus x to the third over 3 factorial came from. Okay, so the first thing that we need to know is f has to have n derivatives, right? So you obviously don't need to do this for like x squared, because that's not that hard to plug into, and it's a polynomial anyway. At x equals c, which again, this is called the center, or the point of tangency. Okay, so it's important for you to know this. So then this polynomial, we're going to call it p sub n. The n tells us how many terms we're going to put in there, or like what the degree is going to be, is just going to be the function evaluated at c plus the derivative of the function evaluated at c times x minus c. And maybe you notice that piece of highlighted so far was the tangent line, just in function notation, right? And then plus we're going to add the second derivative evaluated at c divided by 2 factorial times x minus c squared. Notice second derivative 2 factorial squared. That will always happen, right? Plus, a bunch of other things. The nth derivative evaluated at c times n factorial over x minus c to the nth power. Okay, it's named after this guy Taylor, who was an English mathematician. Blah blah blah. There's more history down below. That derivative over n factorial piece, this is the coefficient, right? It's a number in front of the variable piece, so that is the coefficient. And then there's a special type of this if we center it at 0, right? If the point of tangency is at x equals 0, which is what this is saying here, if the center is at 0, right? C equals 0 means x is 0. Then the polynomial becomes this, right? You're replacing the c with a 0, and it turns into this thing, right? If I replace c with 0, then all these become 0, and x minus 0 just turns into x, right? X minus 0 squared turns into that, x minus 0 to the nth power turns into that, and all these are 0 as well, right? So it's the same thing, just we replace c with 0. And it's named after this guy, Maclaurin, who had some crazy hair. What do we got to say about this? Oh, okay, so if we're approximating, we just make sure we're using the little squiggly brackets there, right? You don't want to say that it's exactly the same. That would be mathematically incorrect. And you can thank Taylor for a couple other really complicated mathematical ideas, such as the integration by parts, right? He also came up with that. So yeah, thanks Taylor. Okay, so let's actually practice doing this, right? So our first thing is we're going to find the Maclaurin polynomial, right? Which this means that it's centered at, like, c is 0, degree of 5, right? So the 5th degree for f of x equals sine x. And then, so let's do that first, right? So basically what we're going to do is we're going to try to find the 5th degree. Actually, I'm going to have to do some work over here. So I'm going to write the 5th degree polynomial, and it's basically going to be f of 0, because we're finding the center 0, plus f prime of 0 times x plus f double prime of 0 over 2 factorial times x squared plus f triple prime of 0 over 3 factorial x to the third plus the 4th derivative at 0 over 4 factorial plus the 5th derivative evaluated at 0 over 5 factorial times x to the 5th. Oops, I forgot x to the 4th over here. And so what you see is we need the function, the derivative of the function, the second derivative, the third derivative, fourth derivative, right? So let's go over here and let's start with the function, right? The function is sine x, right? F prime, derivative sine is cosine. The second derivative, right? The derivative of cosine is negative sine. The third derivative, I'm just going to write it like that, is negative cosine. The 4th derivative is back to positive sine. And the 5th derivative is cosine again. We need to know f of 0, f prime of 0, so we need to evaluate these at 0, right? Excuse me. F prime of 0 is sine of 0, which is 0. F of 0 is 0. F prime of 0 is cosine of 0, which is 1. This is negative sine of 0. Sorry, darn Shenyang commercial. So negative sine of 0. Sine of 0 is 0 still, so this one is going to be 0. This one is going to be negative 1, right? Cosine of 0 is 1, and then you apply the negative, you get negative 1. And then the 4th derivative is sine again, so it's back to 0. and the fifth derivative is back to 1. So you can see a pattern, right? 0, 1, 0, negative 1, 0, 1, 0, negative 1, 0, 1, 0, negative. Like, so you can see the pattern, right? So let's plug these numbers in, right? F of 0 was 0 plus f prime of 0 was 1 times x plus f double prime of 0 was 0 over 2 factorial times x squared, but notice like 0 is just going to be 0, right? So maybe the next one I won't write it. F triple prime of 0 was negative 1 divided by 3 factorial times x cubed plus the fourth one 0, right? And the fifth one, the derivative was 1 x to the fifth over 5 factorial. Cleaning this up and like not writing all the 0 terms, right? We would have x minus x to the third over 3 factorial plus x to the fifth over 5 factorial. And so you can see like this is that thing that we were plugging into our calculator, right? And like once you see the pattern, like do I still need to go and like take a bunch of derivatives here? No, right? Like I can see what the pattern is going to be, and I could write the next like 50 terms and it wouldn't be that hard because I see the pattern, right? But so that's where that thing came from that we're plugging into our calculator that was giving us fairly good approximations. It wants us to find the error of our approximation, right? So we're down here again. Oh, sorry. It says then use the fifth degree polynomial to approximate the value of sine of 0.1 using correct notation. So what we're going to say is sine of 0.1 is approximately P5 of 0.1, which is equal to, we're plugging in 0.1 everywhere here, right? 0.1 minus 0.1 to the third over 3 factorial 6 plus 0.1 to the fifth over 5 factorial is 120. 5 times 4, yeah, 120. Right, and then like I hope you noticed that like we could do this by hand, right? Like I can do 0.1 to the third power. It's 1/10 times 1/10, 1 times 1/10, and then I could do 0.1 to the fifth. It's just 1/10 times 1/10 times 1/10, and you get like 0.00001, and then dividing those by 120 isn't that bad. So like, you know, it is possible to do this by hand, and it's like it's not really possible to do sine of 0.1 by hand, but it is possible to do the polynomial by hand, right? So but I just, you know, like for the sake of time on this video, you don't want to sit there and watch me try to do that by hand, so let's just do it on our calculator. And this is equal to which equals 0.998. Again, I'm going to write the whole thing out so you can see how accurate we are. 334,167. We want to find the error in our approximation. So to find the error, it's basically like the next non-zero term. Right, if you notice we're like adding smaller and smaller numbers as we go here, right? So if I can figure out what the next number that I add is, then like that can't be, that's the error. That's like the most it could differ by afterwards, right? So let's go ahead and quickly find the next non-zero term, which is going to be the seventh one, right? Because the sixth one will be 0. So that's going to be at the seventh derivative evaluated at 0 over 7 factorial times 0.1 to the 7th. So like the important part is the positive or negative. That doesn't matter. It's just going to be, and so just take the absolute value of it because the sign shouldn't matter. So it's just 0.1 to the 7th over 7 factorial. Let's do that real quick. 0.1 to the 7th divided by 7 factorial. Oh, great! It's going to give me that. So this thing here is the most that it could differ by, right? Like the sine of 0.1 cannot be farther away from our approximation, which was this 0.9. This guy, it can't be farther away from sine of 0.1 than that. So what we could write is an inequality, right? So sine of 0.1 has to be in between this number up here, this let me see if I can just copy this number here, way down there. All right, has to be between that, where this number plus the 7th term plus 0.1 to the 7th over 7 factorial, or that number over here minus the 7th term. And it's the 7th term in this case because that's the non-zero term, right? It's not like always the 7th term. It's like the next non-zero term. So we stopped at 5. 6, the 6th term was 0, and the 7th is the first non-zero term. So let's like real quick calculate what this is, so and we can see what it's between. So we're saying, come on, sine of 0.1 must be between, right? So we're going to take, I'm going to do this on the calculator. I'm going to take my approximation and I'm going to subtract the 7th term. So I'm just going to go up and select the 7th term, and that's going to give us this guy, which is 0. Oh, you know what? When I wrote these, this is supposed to be a 0 right here. Right, I just wrote it wrong. It's supposed to be a 0 right there. It's not affecting that much, but 0.09983341667, right? And then if I take my approximation again, but this time we're going to add the error, which was the 7th term, and we're going to get 0.09983341667. Turns out that the calculator itself is out of accuracy, right? So those are the same. So basically, if I do a sine of 0.1, I should be getting that exact number right there, right? So sine of 0.1 is 0.66. Oh, there's a minor difference in there, is there? 998341667. So it's probably just like a rounding thing that the calculator's doing, because all that's different is that 6 at the end, right? Which this has a 7 at the end, and that is a 6 at the end. So it's probably just like somewhere the calculator's like rounding or something like that, just because it's the last decimal. We can see we can get it very accurate. And so just to reflect on this, this is our error, right? And to find the bounds for the exact answer, you add the error to our approximation, you subtract the error to the approximation. That will give you bounds for where sine of, or for what the actual value has to be between those two things. Okay, so let's do another one that's not centered at 0, so you can see what that looks like. We're going to find the Taylor degree polynomial, degree 6 for ln x. So basically what that means is we need the first 6 derivatives, right? So let's start over here. F of x is ln x. We're going to try to find f prime, and then keep going like that, right? The second derivative, the third derivative, the fourth derivative, all the way up to the sixth derivative. So the first derivative is 1 over x, which can be written as x to the negative 1, right? So that just makes it easier to take the derivative. So then we get negative x to the negative 2, which then gives us 2x to the negative 3. Take the derivative of that, we get negative 6x to the negative 4. Take the derivative of that. Hopefully, maybe start noticing that these are like factorials, right? I did 1 times 2 times 3, right? So this 6 is 3 times 2 times 1, which is 3 factorial. That'll come in use later. The next one is positive 24x to the negative 5. 24 is 4 factorial. And then we get 120, negative 120, x to the negative 6, right? And our goal is to evaluate all of these at the center, right? We need to find them at the center. Maybe it's helpful if I just write this out real quick. I'm not going to write the whole thing, but I'll write a few of them, right? So our 6th degree polynomial is f of c plus f prime of c times x minus c plus f double prime of c over 2 factorial times x minus c squared. And you can see that that pattern continues until I get to the term I want, which is f, the 6th derivative evaluated at c over 6 factorial times x minus c to the 6th, right? And so in this case, c is 1. So we need the function and all its derivatives evaluated at 1. So like over here, we need to know, well, what is f of 1? F of 1 is natural log of 1, which is 0. F prime of 1 is 1, right? 1 over 1. Maybe it's easier to rewrite this as negative 1 over x squared, or you can just know that 1 to any power is 1, right? So if I plug in 1 to this one, we're going to get negative 1. If I plug in 1 to this one, we're going to get 2. If I plug in 1 to this one, we're going to get negative 6. If I plug in 1 to this one, we're going to get 24. If I plug in 1 to this one, you get 120. If you're not convinced about that, just go ahead and do it so you can make sure that that's what you get. Because I don't want you to be confused about what we do up here. So let's go and write this one. The 6th degree polynomial approximation is, so this is not where we use squiggly brackets, right? It's only when we're showing the approximation. F of c, which was 0, plus f prime of c, which was 1, times x minus c, plus, oh, x, we know what c is, right? Times x minus 1. Plus the second derivative, which was negative 1, over 2 factorial times x minus 1 squared, plus the third, which was 2 over 3 factorial times x minus 1 to the third. The next one is negative, so let's just say minus 6 over 4 factorial x minus 1 to the fourth, plus the fifth was 24 over 5 factorial x minus 1 to the fifth, and the last one is 120 over 6 factorial x minus 1 to the sixth, right? And then let's simplify this. Remember, let's just go over here real quick. Like this is 2 factorial, this is 3 factorial with a negative on the outside, right? This one was 4 factorial, this one was 5 factorial, right? So like if you're writing this, you could just simplify this to 5 factorial, 4 factorial, 3 factorial, and then these will cancel and just make a little bit easier numbers to work with. You don't really have to do this, but for the sake of us actually having to calculate this, we're going to do it. So the 0 is gone. We're left with x minus 1 minus, this is 1/2 x minus 1 squared, plus 2 divided by 3 factorial is going to be 1/3 x minus 1 cubed minus 3 factorial over 4 factorial. Just like if you think about 3 factorial over 4 factorial, you're going to get 3 to 1 over 4 3 to 1. So we're just left with the 4, right? So 1/4 x minus 1 to the 4th plus the same thing happens with 4 factorial and 5 factorial, right? Everything cancels except for the 5 down here. And the same thing happens here. Okay, and so that's our 6th degree polynomial approximation. What we're going to use it to do is we're going to try to find, well, what is f of approximate 1.1? What is f of 1.1, which is natural log 1.1, which can be approximated by the 6th degree polynomial at 1.1, which means we're plugging in 1.1 up here, right? So let's think about when I do 1.1 minus 1, what are we going to get? We're going to get 0.1, right? Minus 1/2 times 1 minus 1.1 minus 1 is 0.1 again, squared, plus 1/3 times 0.1 to the 3rd, plus 1/4 times 0.1 to the 4th, plus 1/5 times 0.1 to the 5th. Oh, sorry, minus, there's supposed to be a minus in there somewhere. There's supposed to be a minus sign right here. Don't get ahead of yourself. And then the last one is minus 1/6 times 0.1 to the 6th power. And then as you can see, like we can actually, like, so the thing is, like, if you actually wanted to know natural log of 1.1, like you can't do that like in your head, right? So you'd, like, this polynomial you can do fairly easily like without a calculator if you wanted to, like, and it's not, you know, it'll give you a value that's very, very close. So I don't want to do it by hand. You don't want to see me do it by hand, right? This video will be way longer than it has to be for that. So let's do it on our calculator. So we're doing 0.1 minus 1/2, which is 0.5, times 0.1 squared, plus 1/3 times 0.1 to the 3rd, minus 1/4 times 0.1 to the 4th, plus 1/5 times 0.1. Come on. All right. Stop it. 0.1 to the 5th, and then minus 1/6 times 0.1 to the 6th power, and you're going to get this 0.0953101,667. So that's the approximation. You could ask, is it an over approximation or under approximation? Remember, natural log looks like this. It's concave down, which means any tangent line, any tangent function we draw is going to be an over approximation, right? I think that still applies. Let's say natural log of 1.1. So you can see this one's accurate all the way to the 3rd from the last digit, which natural log is bigger, so we actually have an under approximation here, right? So just to review, this one's not asking for it, but I just want to show you real quick. Like if I wanted to know the error, right? If I want to calculate the error, we would look at the 7th term, right? Which you don't have to do all that work for. Just like look at what the seventh term would be, right? It would be 1/7 times 0.1 to the seventh power, right? That's what the seventh term would give you, and then it's going to be a really large number, but with the natural log of 1.1 would have to be in between this thing that we calculated before, which instead of writing out the giant decimal, I'm just going to write that minus 1/7 times 0.1 to the 7th, and a natural log would have to be less than that approximation. When I write this P6 of 1.1, what I'm trying to say is it's this guy here, plus the seventh term, which is, right, natural log has to be somewhere in between those two. And we could calculate what that is, but I don't want to bore you to death. So, maybe do it in your calculator and see what the actual decimals are and make sure natural log's in the middle. Okay, we are not going to do this piece right here, so feel free to use this space up here for what we're going to do next. Sometimes we can create Maclaurin polynomials using other Maclaurin polynomials that we've already created. So we've already created sine, so I could pretty easily recreate sine of 2x. Right? So what I want you to do, and I actually want you to do this, is pause the video, and I want you to list the first 4 non-zero terms of the Maclaurin polynomials for sine, cosine, and e to the x. Right? Remember, you're finding for the derivatives, you only need the first 4 non-zero terms. So it's do it until you get 4 terms that aren't zero. And it's good practice, and these 3 are the 3 most important, and the natural log is the 4th most important, that you have to eventually know how to just know what they are. You kind of want to have them memorized. You don't want to have to recreate it every single time. So please try these before. Okay, so here's what you should have gotten, right? We only need the first 4 terms. So the first 4 terms, first 4 non-zero terms on the sine are the ones we already did, right up to there. The first 4 non-zero ones for cosine is, notice how you get the even powers. It's because cosine is an even function. And then for e, the first 4 terms are just, the first 4 non-zero terms are just the first 4 terms, because you just get this, right? So what I'm trying to show you with this is, let's go back down here, is that if I want to know if I want to approximate sine of 2x, right, then sine of 2x can be approximated by using what we already have. It can be approximated by this thing, the 7th degree polynomial approximation of 2x, which is just simply plugging in 2x everywhere you see an x, right? It's just a substitution kind of thing. And you could simplify that as much as you want to, right? So B, we're going to look at, we want to approximate x cosine x, right? Which, notice we're multiplying our thing by x. So this is going to be approximated by x, the 6th degree for cosine, which is just x times the thing that we had, right? The thing for cosine, the polynomial for cosine was this. And then you can see you could distribute that in there, and you would get that. Okay, and then the last one, same idea. We're gonna do 4e to the x squared, right? So that's gonna be approximated using our same thing up there, but we're gonna multiply it by 4, and instead of x, we're gonna write x squared, right? So we're using the 1 for e now, so it's gonna be 4 times. There's nowhere to plug in anything for the 1. instead of x, we write x squared. So this is x squared squared over 2 factorial plus x squared to the third over 3 factorial, which, you know, this would simplify to 4 plus 4x squared plus 4x to the fourth over 2 factorial plus 4x to the 6th over 3 factorial, and then this would approximate this one. Alright, so you can see how that works. Okay, good luck on the practice set. Please ask lots of questions. Talk to each other.